Hello, welcome back to AP Physics. Continuing on with centripetal force and circular motion, uniform circular motion. One thing I want to remind you of because it's important, when we're talking about an object in uniform circular motion, the net force is going to be equal to the centripetal force. So the magnitude is going to be given by mass times acceleration, the centripetal, and the direction will be to the center of the circle. So when you're looking at the sum of the forces, one of your forces is going to cancel either the x or the y, and the other one is going to be the sum of the forces equal mass times centripetal acceleration. So, for example, here we've got a ball that's being swung around on a string at a constant velocity. The string, and therefore the radius of the circle, is 0.5 meters, and the period is 1.34 seconds. So that's the period, or t. And we're figuring what is the tangential velocity of the ball, what's the centripetal acceleration of the ball, and what is the force of tension in the string. So to figure out the tangential velocity, we use that first equation I gave you, Vt equals 2 pi r over t. This is just a plug and chug, so you get 2.3 meters per second. A sub c, that again is another plug and chug. We just found Vt, so 2.3 squared over the radius 0.5 gives you 11.0. And then we're looking for the tension in the string. So if we look at it, there's no y forces, and the forces in the x, there is going to be a net force, and that net force is going to be equal to mass times centripetal acceleration. So instead of saying sum of the forces equals 0, you're going to be saying sum of the forces equal mass times acceleration. And the only net force the only force that's going on here is that force of tension to the left, which I made my positive to the left. And usually you want to make the direction of positive in the direction of the acceleration. So we said to the left is positive here. I should have probably written that down. So mass times acceleration equals the force of tension. So and the force of tension is equal to 2, which is the mass. The mass was 2 kilograms times the centripetal acceleration, which was 11, and that gives us 22 newtons. So any questions? Okay, no questions. Moving on. This question has got a little bit more interesting to it. So this is a tether ball that's being swung around in a circle, and the angle that the string makes with the pole is theta, and it's got a tangential speed of vt. The radius of the circle that it travels, so it's tracing out the string is tracing out a cone, but the tether ball is traveling in a circle around the path. So we do have gravity here. So when we're trying to figure out what is the angle theta, what does it make with the pole? So mass m. So we're going to start with a free body diagram. There's only two forces acting on the tether ball. We've got gravity down, and we've got the force of tension coming up at a diagonal, making an angle theta. Now, in order for this to be traveling in uniform circular motion, the forces in the y direction have got to cancel. Okay, and the x force has got to be the centripetal force. So we say the sum of the forces y equals 0. So 0 equals, and I said up is positive, cosine of theta ft minus ft, or mg. So because this basically what we're saying is this right here has to equal this. Okay, so the cosine of theta ft equals mg. In solving for ft, you get ft equals mg over cosine of theta. And it didn't tell us to solve for that, but little spoiler, we're going to want that solved for that. So the forces in the y cancel. The forces in the x do not cancel. That's my net force. That's my to the center of the circle is my my centripetal force. So we're going to say the sum of the forces equal mass times acceleration, or centripetal acceleration. So MAC, okay, equals, now again, we've only got one force in the x direction. That's this horizontal component of gravity. So that's the sine of theta ft. Okay? And then, so plugging in for that, mass times the centripetal acceleration equals sine of theta ft. Now we're going to go ahead and substitute in for ft, mg cosine of theta. And what we get is a mass times a sub c equals the sine of theta over cosine of theta times m times g. Our m's cancel. And we're going to go ahead and substitute in for a sub c, because a sub c equals vt squared over r. Okay, and what we get is that the tangential velocity equals the root of rg times the tangent of theta. Oh, I forgot to mention that we collapse the sine of theta over cosine theta into tangent of theta. So that is that. Working that without numbers. And again, I'd like you to be kind of used to working these things with variables and not necessarily numbers all the time. When you do your homework, try to work it with variables first and then substitute numbers in later, because that's the test is going to have probably more focus on variables than the numbers. Okay. Another problem here, we've got a penny on a record. It's a distance r away from the center. The coefficient of friction between the penny and the record is mu. What is the fastest tangential speed the penny can have before flying off? Given terms of mg, r, and mu. Solve for vt. Okay, so like normal, what we probably want to do is go and start out with a free body diagram. So we've got gravity pulling the penny down, so force of gravity equals mg. We've got, I don't know why that's a t, that should be an n. We've got the normal force going up, and then the inward force is going to be the force of friction. That's going to be what's keeping the penny from flying off. That is my centripetal force. So we're going to go ahead and say that the forces in the y direction cancel. So 0 equals, and again I said up is positive, ft minus fg. Ft equals fg, which we already knew that because we drew hash marks here, but that's the full process. Then we want to say the forces in the x, that has to equal my centripetal force. So so some of the forces in the x direction equal mass times acceleration. So mass times acceleration, centripetal acceleration equals the force of friction. Now you guys remember that the force of friction equals mu times the normal force. We just, why did I make that ft? That should be fn. This should be fn. I don't know why I put ft. Just go with it. It's going to solve out anyway. So f of f equals mu fn. That equals fg. Fn equals fg because of this. Fn equals fg. And Fg equals mass times gravity. So the force of friction equals mu times mass times gravity. So substituting that in for the force of friction, we see that the masses cancel, just like the last time the masses canceled, which is kind of interesting. There's a lot of times where mass will cancel out in a physics problem. Certainly not all the time, but quite frequently. Depending on what you're doing. So, and then a sub c we know is equal to tangential velocity squared divided by the radius. So substituting that in equals mu g. And then finally solving for tangential velocity, that is equal to the root of r mu g. So this is the maximum speed when all the forces are perfectly balanced. Friction is maxed out. Remember, this is my maximum friction. So this is spinning at a tangential velocity where the friction is maxed out. Okay. Another problem. Here we've got a rider on a not a roller coaster but a ride, and it's one of those rides. Six Flags used to have one. I don't think that they have it anymore, but it was a big drum that you would spin around in, and then the floor would drop out. And then you could stay stuck to the wall if there was enough friction. And the question is, what basically is going on with the forces, and what coefficient will keep a person from sliding down when the floor drops? So and then we throw some numbers at it. So looking at this, so we've got the mass times gravity, the force of gravity down. We've got the force of friction is preventing the person from sliding down, which means it's acting up. And then we've got the normal force between the wall and the person acting to the left. And which of those is going to be the centripetal force? It's the normal force acting to the center of the circle that's providing the centripetal force. Friction is just preventing you from sliding down, if you can prevent from sliding down. So what we're going to say is that we know that the forces in the y direction cancel, and the forces in the x direction here are going to be equal to the centripetal force. So y cancels, and basically what we're saying is the force of friction equals the force of gravity. They balance. So substituting in, we get mu times F of n for a force of friction, and mg for a force of gravity. And we solve, and we're solving for Fn, we get F of n equals mg over mu. Sorry, a little crowded there. Mg over mu. Then we say that the forces in the x direction equal mass times centripetal acceleration. Okay, so ma sub c, and as we already said, our centripetal force is going to equal to the normal force, which we just found up here was equal to mg over mu. So mass times mvt squared over r equals Fn. Okay, substituting in for here, mg over mu. Strange enough, the masses cancel out again, and we get that Vt squared equals Rg over mu, or Vt equals the root of Rg over mu. Putting in some numbers, finding the tangential velocity, we get Vt equals 2 pi r over t, gave us the radius is 2.5 meters, and the period is equal to 1.5 seconds. The tangential velocity is equal to 10.5 meters per second. What's the normal force? That's equal to m times a sub c, or mvt squared over r. Since we know vt and m and r, we'll plug those in, and we get that the normal force is equal to 3070. I'll spit it out. And then lastly, what's the coefficient of friction? Based on that, mu Fn equals mg. So plugging in for the Fn that we just found and mass times gravity, we get the minimum coefficient equals 0.22, and that of course does not have units. Okay, so if you picture yourself spinning around that ride, you feel like something is pressing you to the outside of that wall, although there's no force that's acting to the outside of that. There's no force that's pushing you to the outside, although you feel like something is pushing you to the outside. That's because the normal force is pushing you to the inside, and sometimes our feelings aren't exactly reflective of what's really going on. So the feeling of weight or weightlessness or that kind of thing comes from the forces that are at work on you. For example, when you in an elevator and it starts to go upward, you tend to feel heavier. After it gets going, you feel normal. When it's going up and slowing to a stop, you feel lighter. And if the elevator cord is cut, you feel scared, or weightless. Probably a little bit of both. Okay. So when you're stationary or moving at a constant speed in an elevator, the normal force and the force of gravity on you are balanced and you feel normal. Okay. In order for you to accelerate upward, there has to be a net force on you upward. Gravity doesn't get weaker, the normal force increases on you. Okay. It's that normal force going up that makes you feel heavier, like something is pulling you down. Okay. It's related to your inertia. Your inertia wants to stay put, but the elevator is accelerating you upward, so you feel like you're being left behind, like something is dragging you down. When you're moving upwards and slowing, that normal force decreases because there's a net force on you downwards. If you're moving up and slowing, the net force is down, and that normal force is decreased, so you feel lighter than normal. So it's not that you're actually lighter or gravity is any weaker on you. If you're being swung around, and this is a little weird, if you put the elevator cord on the side and swung it around in a circle, this would be like that Tom's Twister ride that we were talking about. The normal force would be pushing you to the center of the circle or left from this picture, and you would feel like something is pushing you to the right. So basically, you often feel like there's actually a force that's opposite the direction of the force really acting on you. And that relates to why spaceships are often seen in sci-fi movies as rotating, or not often, but periodically they're seen as rotating. Um, so picture this is the inside of a spaceship, and this is space, and this is the floor, or whatever, the wall. Okay, and if you were why is that not rotating? There we go. So if you were in a rotating spaceship with no gravity, would you still need a centripetal force? Would you still need an inward force if there was no gravity? Sure you would. Otherwise, you'd just travel in a straight line. Um, so what direction is that centripetal force? That centripetal force is always directed to the center of the circle. Now, from your perspective, the center of the circle is always what direction? It's always the same from your perspective. It's always up. Okay. So, so from your perspective, the centripetal force is always up. Okay. Now, because you've got a force that's pushing you up, okay, you feel like something is dragging you down. You feel like there's artificial gravity. And so that's why those spaceships are sometimes seen spinning, so they can create an artificial gravity. How would you increase the artificial gravity on the spaceship? Well, without changing its size, you would increase the rate of spin, and you can if you can picture this just being like pulled down to the ground mercilessly to your knees from this artificial gravity. And of course, you're not being pulled down to the ground; you're being pushed to the center. Okay. So if we compare the artificial gravity based on these two people, we've got two different spaceships, one with a larger radius as opposed to the other one. What's the same for these spaceships in terms of the centripetal motion or uniform circular motion? They have the same period, but they have different radii. So if we look at this equation, if they have the same period, and this spaceship has the greater radii, it's going to have a greater centripetal acceleration, and therefore a greater artificial gravity. So now, based on this, you're actually, based on this, as you're rotating around, the gravity on your feet, because it has a larger radius, is going to be stronger than the gravity that's on your head. Not by a ton, based on this example, but the gravity would be stronger on your feet. And then there'd be some other weird things that would happen that are distinctly Earth-like gravity-like. For one, if you were to jump up, would you come back to the ground? You would come back to the ground, but you would. Do I animate this? Okay. Well, what you would do is you would jump up and you would move off at a diagonal. If you were moving to the left and you jumped up, you would move off at a diagonal. And then you would get further away from the floor as this distance increases, and then you would get closer to the floor, and then as this decreased, and you would come back to the floor. The only thing is, depending on the spaceship and how you jumped and all that stuff, you could come back sideways. You could land sideways, so you could jump up and land on your side. Wouldn't that be disorienting? You could also do something really, really cool. If you were spinning around on the spaceship and you threw a baseball exactly opposite the way that you were moving at the exact same speed, okay, you could throw a ball and it would just sit there. It would be moving, it would be stationary from an absolute frame of reference. But from your perspective, it would come back and hit you in the back of the head, or would it hit in the back of the head or the front of the head? I guess it depends on which way you were facing. So there'd be some interesting things. Okay. That's where we'll call it a day.